Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. In this lecture, we're going to take our first step toward understanding object detection. As you'll come to see, this is actually a multi-step process. So why do I say this? Well, so far, we have only done one task with CNNs. That's classification. That's where we feed an image into the CNN, and the CNN tells us what the image is of. For example, it could be a cat, dog, or a rabbit. But what if we have an image with multiple things in it? As you can imagine, this is probably the most realistic scenario. For example, if you're building a self-driving car, the camera is going to take pictures of the environment, and it's going to have to recognize a lot of different things: people, cars, bicycles, traffic lights, traffic signs, lane markings, and so on. So classification by itself is sort of a very limited problem. But now we're getting ahead of ourselves. What if we want to, let's say, just go one tiny step further? Well, then what we get is this problem of object localization. As its name suggests, this is the problem of not just determining whether or not an object is in an image, but also its location. Typically, this is done using bounding boxes, or in other words, rectangles. But there can be other variations on this, such as using ellipses for faces. You can have actual facial key points. This is called landmark detection, and so on. So in other words, now we don't just want to know what it is, we also want to know where it is. So how does this change the code? I think you'll find this to be pretty intuitive. So recall that what we've been doing in this course is using state-of-the-art feature extractors and adding logistic regression on top of that. Well, predicting the coordinates of a rectangle would be regression rather than classification. So instead of just adding a logistic regression on top of our ResNet, we can add an additional 4 linear regressions. These will predict the x and y coordinates of the center of the rectangle and the height and width of the rectangle. Now some details if you wanted to try to implement something like this for yourself. Instead of using the absolute coordinates of the bounding box, what we usually do is normalize it so that they're always between 0 and 1. For example, in this image, the x center is about 0.45, just to the left of the middle. The y center is about 0.3 or 0.25, closer to the top than the bottom. Remember that in programming, we usually use the top left as the origin. The height is about 0.5 of the total height, and the width is about 0.35 of the total width. Another consideration is, what should the loss function be? Now that we are no longer doing just classification, our loss can't just be the cross entropy. So to understand this, first we have to understand what the targets and predictions will look like. These will now be the number of classes plus a few more dimensions, rather than just the number of classes. First, we have a target for telling us whether or not there is even an object in the image. As you can imagine, some images just won't have any objects in them. For this, we can use binary cross-entropy. Then we have the multi-class cross-entropy for the logistic regression. The length of this part will just be the number of classes. So if you want to recognize people, motor vehicles, bicycles, traffic lights, and stop signs, then the number of classes would be 5. Finally, we have 4 regression outputs for the bounding box. For this, you could just use squared error, but the Huber loss is also a common choice. Now, of course, you could also just get rid of the binary indicator for whether or not there's an object, because you could just consider no object to also be a class. Then you just have the multi-class cross-entropy plus regression loss. Note that when you don't have an object in the image, then the regression targets shouldn't contribute to your loss, so you have to make sure that the regression loss is 0 when there is no object. Similarly for the categorical cross-entropy, if it doesn't contain the no-object class. Because we have multiple components to our loss function, we still need to think about how to minimize the whole thing. Remember that we must have a scalar loss in order to have something to minimize, and so the solution is to just add the 2 or 3 depending on how you structured your output. You just add them together. Importantly, you have to decide how to weight each of the factors, which basically is just a matter of trial and error and maybe some cross-validation. It's a hyperparameter just like any other. This idea of weighting losses will appear again when we talk about style transfer. So that's everything about object localization. To summarize, this is our first step away from the basic task of simple image classification. However, we are still far away from our final step. What's interesting is that even if object localization is not your goal, it has been shown in the past to improve image classification results. So even if you only care about image classification, you might not want to just build an image classifier, but rather an object localization network. Intuitively, this might help because once your CNN focuses on where in the image an object is, it can focus its efforts on classifying just that part of the image rather than trying to do a classification over the whole thing. In the next few lectures, we'll look at how we get from object localization to object detection.